That's the logic. That's how I remember it. So this means if I have a product of phi of x, product of phi of x, and I want to have the normal ordering, or let me just even consider not the full, all the terms, let me just consider phi plus. Okay, so phi plus contains A and phi minus. This is simple example. Okay, just one term. If I have a term phi into phi, I would have phi plus phi minus into phi plus phi minus. So I would have 4 terms. Okay, so I have thrown away 3 terms and I have just picked up only one of them to which explains our point. So if I have phi plus phi minus, then this guy contains an annihilation operator and this contains a creation operator. So this means its normal ordering would be plus minus phi of minus x into phi. So here, if I replace my phi by psi, the Dirac-Spinner psi, which is a fermion, so then I would have a minus sign here. Okay, for a bosonic field, I would have a plus sign here. So this guy comes to this side and minus contains the dagger. So this is A dagger A. Okay, this is how I remember. I also forget it in terms of plus and minus components, but I remember that the normal ordered quantities, A dagger has to stay to the left and A has to stay to the right. So whenever we do field theory of any kind, actually right from the Lagrangian all the way to Hamiltonian, all the way to anything that you derive in field theory, it is assumed a priori that everything is normal ordered. Without stating so explicitly again and again, it's always understood that you will normal order the things at the end of the day. Okay? And because the theory that we are going to construct, the string theory is also a string field theory. It's a string field theory of one-dimensional objects instead of a field theory of zero-dimensional objects. That's the only thing. So all these techniques, they stay there. They hold true, but with proper generalizations. Okay? So that's the only way to do it. And that's why I always come back to these very elementary ideas of field theory, because they are the same in field theory as well as in string theory. Okay? So normal ordering we know, time ordering we also know. Therefore, now we are able to talk about this interaction term. So in the Lagrangian, it will be the same term with the opposite sign. So here, in any case, the interaction Hamiltonian occurs here, and it depends on how many. So at x, for a second order diagram, for a first order diagram, there would be only one x. There would be only one vertex. Number of vertices decides the order of a Feynman diagram. So here it's at the same point x, 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 and 3 borderlines meet at a vertex. Now you can easily see, supposing I decompose it into the positive and negative frequency parts, I do the same here, I do the same here, then these are 2 terms, these are 2 terms, these are 2 terms. So if I multiply them all, I would have 8 terms. 2 terms into 2 terms would be 4 terms, into another 2 terms would be 8 terms. So, and these are first order vertices, first order diagrams. Then you have second order diagram, there would be 2 of them. This is the nth order term with n vertices. Okay? So, to this interaction Hamiltonian, one can write down 8 fundamental basic vertices. So Now, this is a electron scattering with the emission of a photon. This is positron scattering. So positron is going this way. When I depict it this way, it goes to the other way. Okay, and this is with the emission of a photon, with the absorption of a photon, and here I have E minus and I have E plus. So E plus is actually going this way. The positron is going this way. So this is pair annihilation, and here it is the pair creation. Now, so this is electron scattering. This is positron scattering. This is the electron positron annihilation, and this is the electron positron creation. And in each four of them, there is a absorption of a photon. I can have another four similar diagrams, but the only difference would be, now this would be photon is being emitted, photon is being emitted, so electron-positron pair creation with the emission of a photon, electron-positron pair annihilation with the emission of a photon, positron scattering with the emission of a photon, electron scattering with the emission of a. And if you write down, if you multiply these three terms here, you make their you write them in the component form: positive and negative frequency parts, positive and negative frequency parts, positive and negative. You can actually identify, so you will have 8 terms here, and you can identify which term corresponds to which of these diagrams. One term would correspond to one of these, another term would correspond to another of these diagrams, and so on. So all these 8 terms you can identify with these 8 diagrams. Now, the point is, this is what we are doing in quantum electrodynamics. Supposing I were doing electroweak theory. Now, the first expression for the S matrix would remain the same, but the definition of H interaction given by this would change. Okay? Now, this definition holds only for QED theory, not for electroweak theory. For electroweak theory, I can write down a counterpart corresponding to this, which we would not be doing, but we understand the point that for electroweak theory also we can write down an interaction Hamiltonian, and then we can make similar expansion. You can go through the standard textbooks on quantum field theory, for example, Louis Ryder or Mendel and so. These are my very favorite books. And of course, for these things like Dirac spinors, the book, the first volume by Bjorken and Drell still remains unbeatable. This is the master book from which many books have originated. Of course, its volume 2 deals with all other fields like scalar field and vector field, but this volume 1 deals only and only with the Dirac field. So, of course, the title of the book is Relativistic Quantum Mechanics, but actually, so what you do, as I told you last week, that the only difference in relativistic quantum mechanics and relativistic quantum field theory lies in the sense that in relativistic quantum mechanics, you derive single particle relativistic wave equations, whereas uh, following the basic principles of mechanics, which is discrete. Okay, in quantum field theory, you construct the Lagrangian density or the Lagrangian or the action of a theory. You use the variational principle, you derive the equations of motion, and these equations of motion are identically the same that you derive in relativistic quantum mechanics, but the interpretation now is different, that now this field, these appearing things like psi would now be a Dirac field, Dirac spinor field, a four-component Dirac spinor. This would be an electromagnetic field. You can derive all those Maxwell's equations out of that. But here they would be field equations. In field theory, they are all field equations. That's the difference. Okay. So I could do the same thing for QCD theory, quantum chromodynamics, theory of a strong nuclear force. I can again, my first expression would remain the same, but the definition of this interaction Hamiltonian would change, and then I would construct the number of, I will have to see how many terms I get, and then I would write down the first order Feynman diagrams for the QCD theory, and then we know the result that these first three theories, the quantization of these first three theories, construction of quantum field theories corresponding to these first three forces, electrodynamics, strong and nuclear forces, goes perfectly well. There is absolute